Thank you all very much for having us here. I'm a huge fan of the ACM. You guys have great events. Also, I like the fact that you take a moment to look at who has new jobs to offer. A lot of people in this industry are making career changes, changing their skills, picking up new skills. And I just want to say, for those who are, not only do you have a lot of company, but actually the entire industry is undergoing a career change right now. So it's a great time to be doing new things, because basically everything's new, everything's changing very, very fast. Okay, so thanks for having me. I want to talk to you about streaming architecture. Let's see if I can get the clicker to work. This is my contact information. Yes, that's the first. This is my contact information. I'll repeat that at the end. Now, let's look at new ideas. Until recently, I would say for most of my life, if somebody talked about a vehicle, a wheeled vehicle in space, a car in space, I would envision something like this. This was an astronaut driving around on the moon in a vehicle, and that was kind of the image most of us had for a lot of years until about a month ago. And of course, now we think of this when you say car in space. So things change. There's a lot of change going on. And it's a way to plant a new idea, to think about things in a new way. And that's what I want to do very briefly here with you today, is just plant a new idea. Now, I don't have anything as shiny and impressive as a big red car floating around above the earth, so you have to use your imagination a little more. But here's the idea that I want to plant in your heads today, and that is, what if you use a stream, a message stream, as a kind of central source of truth in your architecture, rather than a database? A lot of people think of that database as where all the shared information is, a thing that you go back to. But what if it were a stream instead? So let's jump into an example and see how that might work out. Now, this is just a little toy example to help you think about how these things could work. If you had a fraud detection system, you have a model that's looking at current events with a card use. We talk about credit card velocity, meaning if I make a purchase right now here in Santa Clara, and 10 minutes from now I make a purchase in Moscow, okay, something's wrong, so it's probably not me. But we would be comparing the current event. We would be having that model also look at a database that would have a history of previous card use. Okay, but what happens when you scale up? You may have a number of models who are accessing that same data, and what can happen is you start to put pressure on that database. It's too much traffic, too many people trying to use it. Another problem is flexibility. There can be big disagreements about the schema. If somebody wants to change, somebody wants to start something new, it's a shared resource, and that makes it much harder to do. So it puts a bit of a pressure on that database, and it's kind of a traditional way to look at it. But what if you just make this one change, that you take that information and you put it out into a message stream? I'm using this horizontal cylinder to represent a message stream, streaming transport. And you're basically still doing the same thing. You have a process that would update that database. You would still have last card use. Everything would work in the same way, but now you've stuck a stream in there, kind of in the middle of it. And why that matters is suddenly you can share that information to other consumers, to other projects. Maybe somebody wants to use it for something else that they want to do with card location history, maybe an entirely other use. So you have these other consumers that are sharing the data in the stream. And in fact, one of the other consumers might be you. Maybe you've just rolled out a new model, a new implementation of your fraud detection model. And this makes changing implementation, rolling that out, much easier to do because of isolation. And so you can basically roll out a new model. You're still working with the same data. Even if you're in production, you're not interfering with what's going on in production. And when you want to make the new model go live, it's very easy to do that. So this sense of isolating or separating services, of course, is a pattern of microservices. And so part of the idea that I want to plant today is that stream transport supports microservices. A stream, if you have, for that messaging technology, if you have the right capabilities, not all message transport will do this, but if you have the right capabilities, that really supports the flexibility of a microservices style of architecture overall. And that gives you a lot of advantages in terms of flexibility, a lot of advantages in various ways. So what we're really saying is A lot of people, when they first think about using streaming data, they're thinking about it as data that's coming in and being used in some sort of a real-time application, maybe to update a real-time dashboard, something like that. And why would you use the stream transport? Now, I'm talking about the message transport, not the stream processing. Why would you need that? Well, in a way, it's sort of a safety bucket upstream. You have streaming data coming into your real-time application. If there is some interruption, you want to be able to keep it. I think that's the first one that people begin to think about using these technologies. But with the right kind of architecture, it suddenly opens up some very different possibilities, even beyond that real-time application, because you have that message transport at the heart of your overall architecture. And here it opens up other kinds of use cases. I've taken the example of maybe medical data coming into a stream. Yes, maybe you have some sort of real-time analysis going on, but you also may want to be updating, say in this class B at the top, maybe these are searchable documents. Maybe that is a database. You're basically looking at the status of the events at the moment. In other words, you're mutating that data in the database to keep saying this is the current situation. But again, if you have the right capabilities in that message transport technology, you also can have use cases like Group C at the bottom. In this case, we said it might be used for an insurance audit, but what we're really saying is if you have the capability to replay those events, if you can do it over a long-term history, then you have a long-term event-by-event replayable history. And that's useful in a number of different ways if it's really practical to do it, and it is with the right design, the right technology. So this changes the way people begin to think about streaming. They're not just using it for real time, they're using it as a very flexible, a very, in some cases fast, a very agile way to deal with data across a wide range of different systems and different applications across your organization. So let's take a moment and think about, I said it matters if you have the right capabilities in that stream transport, and what do we mean by the right capabilities? Well, stream transport that works in the style of Kafka, we'll say Kafkaesque stream transport, fits what you need to be able to support streaming microservices. Now, what technologies do we know of that have those capabilities? Well, let's see, hand in the audience, right, one of them is Apache Kafka, which is a lot like Kafka. The other is MapR Streams, which uses the Kafka API. It has those same capabilities that are needed for streaming transport. It has some features that go a little beyond what Kafka can do, but either one actually has the basic capabilities that you need to get that sort of flexibility. And what you're really looking at is you need decoupling between the data sources, labeled P here. You have a number of different data sources coming into a stream. You need to be able to handle that. You need to be able to handle a number of different consumer applications at the same time. These are probably going to be consumer groups, not individual consumers. And you need decoupling. You need isolation between the data sources and the consumers. Indeed, you need isolation between the consumers and each other. And not just in terms of being able to implement a new consumer, but you need isolation or decoupling in terms of time. And so what we mean by that is you want the data, the message, to be available to the consumer right away. In many cases, these are low latency or real-time applications. But you don't want to have to use it right away. This is not a transport system that broadcasts data to the consumers. Instead, the consumers are basically subscribing to that data. You want to be able to do this at very large scale. You want to be able to do it with very high performance. You have to have performance, but you also need persistence. And that's what gives you that decoupling and decoupling in terms of time. If you have persistence of the message, even at high performance, even at large scale, what this means is that a consumer doesn't even have to be online at the time the message shows up in order to be able to use it. You can add a consumer later. You can have a consumer that's not running at the time. And that's how you get that very large degree of flexibility, of agility, ability to implement new things very quickly. And most importantly, that isolation of the consumers from each other, so that they aren't interfering with each other. And that means you can be rolling out new things, you can have people sharing data, even in production. So what you want for good streaming for this type of microservices approach is you want streaming that is persistent, that's performant, and pervasive. We're talking about this across a wide range of different systems within your organization. Now, I've referred to MapR streams as one of the examples of a stream transport that can do this. Like all capabilities in the MapR technology, they all use open APIs, in this case Apache Kafka. MapR streaming transport, like its distributed files and its NoSQL database, are not separate components. They're all part of a single technology. They're all part of one system, literally the same code. So unlike Apache Kafka, when you're using MapR streams, you don't have to run a separate cluster for the stream transport. You're actually doing the transport on the same cluster where you're storing data, where you're running applications and so forth. So that is one difference. There are a few other differences, but the style is still the same in terms of being able to support microservices. This was a quick example for me to remind you that this is all one technology. This is actually Ted's home directory, and you look in there, you see directory, you see files, table streams. These are all within one directory. It's literally the same code, the same technology. Now, one other feature that MapR Streams has is a little different than Kafka, opens up another set of use cases, and that is that MapR Streams has very efficient, multi-master, omnidirectional replication. And what this can mean, especially to an application developer, is that you don't have to worry about where data is. You want to think about your application, what you want to do with the data, not necessarily where it's located. You want to leave that to the IT and system administrators who have to worry about where data is and can worry about data locality, who has access and who does not. So because MapR Streams has this ability to be replicated, you as the application developer may not be in the same place as the data. You can just have a replicated stream. You're basically using the same data. It's very efficient, very easy to administer, and it gives you this separation of concerns between the system administrator and IT and the people who are developing applications. And that makes everybody's work, goes a lot more efficiently. We find that people are using capabilities like this, and so might you want to basically build a global data fabric where you have true multi-tenancy, you have access to data wherever it is, you have the ability, a fine-grained ability to find data and also to be able to control whether people do or do not have access. Maybe the thing that's connecting this data fabric is a stream. It's not the only way to do it, but it's a very efficient and quite a new way to do it. And this gives you the ability to very easily administer it as one single thing, and yet you can go in like finding any thread in a fabric, locate exactly the data that you need, and do that very efficiently. So let's take a moment or two and just quickly look at some use cases. How can this play out in different sectors and different industries? We take the example of people working in ad tech. There they have the challenge that basically their inventory, the currently available ads where bids are going on, this has to happen very, very fast. You need a very accurate understanding of what ads are available, but you often have this happening across different data centers, and they may be independently handling their billing. If you handle that inventory basically through streams and you have stream replication across those data centers, it really simplifies that problem. Telecommunication industry is another example where this can really pay off to make use of streaming as a main part of the architecture. You have callers interacting with cell towers interacting with each other, interacting back to central data centers. Often they're intermediate data centers. We certainly see that with a number of our telco customers. And you may need to send aggregates of data to intermediate centers and back to central for billing. You also need to be very responsive. If suddenly some event is going on, you may want to be able to retune a tower toward that event. You need to be able to do that with very low latency and to do it very efficiently. So in this case, if you're doing this data location and data collection and getting it back to intermediate and central centers, if you're doing that as a batch process, it can take up to 30 minutes per hop. So if you're trying to retune a tower to some event that's suddenly happening and you've got 2 hops, that's not going to work very well. If instead you handle that via streams, via streaming event, and in the case of MapR, using stream replication, suddenly reduces that latency to seconds or sub-seconds. It totally changes the way you can respond to events as they happen. It also is more efficient for getting data back to Central for billing purposes. Now, another aspect of MapR streams that's slightly different and affects the use cases is just like Kafka, you assign data to a topic. That's very useful in both cases. You can label that topic in a very understandable way that helps you find the data that you have. With MapR, however, and because it's all part of one system, it's all distributed across the cluster, you can have hundreds of thousands of millions of topics rather than by the time you're getting up to say 50 to 100 with Kafka, you start to have to add more machines. So it's a little bit of a different thing in terms of how fine-grained you can make your use of assigning data to topics. Because you do have so many topics, or you can have so many topics with MapR, there is a first-class object in the file system called a stream, which is where you apply policies, time to live, whether you're doing replication, who has access and not. But other than that, it's that same principle. So quickly looking at a couple of different industries, with IoT data coming from a number of different sensors on different pumps, say you have an oil and gas exploration system, all of that can be handled through a single stream. You have many, many topics, but it also means on the consumer side on the right is that not all consumers have to use all of the topics, all of the streams. And you can basically have some that are using all streams, some that are using a few. This way you can actually handle that data through the same system, even where you have individual customers who should not have access to each other's data. So I want you to think about the topics as an organizing principle. We look at a use case from financial services. I think this was data from New York Stock Exchange transactions. You can actually build an application that is a transaction exploder so that you're really assigning very fine-grained assignment of different topics, data to different topics, and that changes the way you do queries. And in this case, that sort of exploded by topics view is kind of taking the place of what a database is doing and giving you a lot of advantages by doing that. Similarly, in modern manufacturing, I just have these pictures that happen to come from the University of Sheffield, which has an advanced manufacturing research center, just to remind me to talk to you about manufacturing. But they have a similar situation. Not only do they have a lot of IoT data, but they also have to do a much more mundane thing of being able to track a lot of parts. And when you're doing assembly, say assembly of an aircraft, to be able to do that in different layers of assembly, you have to be able to figure out where your parts are and keep track of all of that at the same time. So again, things that you might have traditionally handled in a database, the database now becomes this. We're not saying don't use databases. We're saying use that as the optimized, specialized thing for a particular kind of local project and have that big central shared source of data be the stream. So we talked about all this. Streams can be advantageous over a database in certain situations because they're faster. The operations are also simpler, and that makes it much easier to share data because the new data is coming through event by event, but you're not mutating the data that's there. And so that can make it faster. It also means that you don't have to commit to a single kind of database. You can have updates that are coming through a stream that are shared. Individual groups can use the style or type of database or optimize the database individually for what they're doing. I'm going to skip ahead because we are a little short on time here. MapR also sees a lot of use cases where people are wanting to do some edge processing, especially with IoT data. If you do that, we have a small footprint cluster.
Don't worry too much about time. We can be flexible on that.
All right. All right, thank you. So MapR also has a small footprint cluster because we see a lot of people with IoT data who want the option to be able to do some processing at the edge. And then they can send all of the data or aggregates of the data or process data back to the center, again, taking advantage of stream replication. So I just want you to think about this as a different way to think about your architecture of when and why would you use streaming data and use stream transport. It's not just to supply data to a real-time application, but it has really advantages and ways to use it that go far beyond that. In the case of this edge processing, we have a number of different customers who are using this. I'll just take the example of the medical one, the third one down. Hospitals and medical testing facilities increasingly are using machine learning to assist human decisions about, say, imaging data. And so a decision cycle that might have taken 12 hours to get an image processed and somebody to read that image and bring that information back to the physician making a decision, that can now happen in under 15 minutes. And this is an example that says it's not just that things happen faster. When you change in these ways to have this greater flexibility, this greater cycle of being able to ask a new question and a new question without a big mountain of the need for IT intervention in between, that kind of agility and that kind of flexibility lets people interact with data in a different way. It's almost like breathing, kind of at the rate that they can think, interpret something, decide what their next question is, kind of a natural way to reason from data. Now these systems can actually support that. And so it really is changing the way people are drawing insights from data across a number of different industries. And we've talked about some of these ideas in a different little short book called Streaming Architecture. O'Reilly sells them, but you can read a copy online or download a PDF through MapR. Ted and I have also just written a chapter in the Encyclopedia of Big Data Technologies called Streaming Microservices, and we go into much deeper detail about some of the ideas that I presented. So now I just want to shift and introduce what Ted's going to talk to you about. Machine learning has become much more widespread and much more mainstream. It's not just a specialized thing. But the question is, how do you make machine learning successful? A number of people ask, what's the best tool? And there are some really great tools out there. They're not all equal, but there's some good ones. We love H2O. MXNet is good. People are widely using TensorFlow, Caffe, many different things you can think of. What we find is that our customers who are the most successful with machine learning don't use just a single tool. They keep 4 or 5 or 6 in their toolkit and use those regularly. It's not just differences in preferences of their different data scientists. It's that no single tool, it's not that they're all equal, but among the good ones, no single one fits every situation. But it turns out, one thing that does cut across all of those different tools, all of the different projects, is that you have to be able to handle the logistics, to handle the data, the input data, preparation of data, make it available, what do you do with the output, how do you handle the many, many models, the hundreds of models you have. And if you can't do that efficiently and do it in production, really your machine learning becomes an experiment rather than a useful central part of your business. So it turns out the thing that's most important to make machine learning work is to be able to handle the logistics. That's probably where 90% of the effort goes towards success. And Ted's going to talk to you about some new designs that build on this idea of streaming microservices, taking advantage of that in the machine learning arena. And so a lot of this content is from a little book we were giving away. Again, you can read a copy of that via MapR. We've also written a chapter for the new encyclopedia talking about a rendezvous architecture that Ted's going to talk about now. Please continue and help to support women and all types of diversity in tech. It's not just good for those individuals, it's actually good for society. Excuse me. And as one woman in tech, I say thank you very much.
So I'm going to talk about machine learning logistics. What Ellen was talking about earlier was how streaming forms a very, very useful large-scale organizing glue for streaming microservices. Now that's in contrast with synchronous microservices where you have a call and a response. And the interesting thing that we're seeing is that as we scale these large systems bigger and bigger, it isn't that everything gets bigger in proportion. What's happening is that we have changes in preferred topologies and shapes. So just like if you have one of these little animals that strides across the water, if you made it the size of an elephant, it would never float on the water, and it wouldn't even be able to stand up. On the other hand, if you made the elephant as small as the water strider, it would be very, very inappropriate and suboptimal. It probably wouldn't be able to breathe properly because, again, the change in the ratios, the design ratios, which leads to a different architecture for the animals at different scales. And we're seeing the same sort of thing with computer systems. There are different architectures at different scales. And at larger scales across distance and across time and across speeds, we're seeing that different kinds of connective tissue, different shaped legs, are more appropriate. In particular, streams connect services very, very well. Now, what I'm going to talk about today is a more detailed example of that. So, I'm Ted Dunning. I'm Chief Application Architect across the street, and also a committee PMC member and newly re-elected board member at the Apache Software Foundation. Happy to answer questions about any of those, or how to become an O'Reilly author, or whatever. But today, what we're going to talk about is machine learning. Now, here's the traditional view of machine learning. You take old data, you take a magical training algorithm, TensorFlow or whatever, it's so exciting and exotic and magical, and you get something called a model. A model looks like a big hunk of data. But that hunk of data becomes a program, and you give it more data, and it makes decisions for you. And hopefully that, of course, leads to world domination and glorious riches and so on. But the basic idea is that this is a new style of programming. That's all it is a different way to write computer programs based on examples, rather than based on specifications, or the way some of us program based on gut hunches. But the idea is that you do not necessarily know exactly what the program should do. You know it when you see it, but you can't necessarily say it in advance. And as a result of that, we can't deploy or trust this same software in the same style as we can with conventional software. We don't have unit tests because unit tests depend on the program doing what we intended, and we don't know what we intended. We intended to do whatever was right. And that's a really hard unit test to make up. You say the unit test is find fraud in new data. It's like, that's not a unit test. And that means that the logistics are different than normal programs, and they become much, much more complicated and more difficult. And a sad but true fact, a sad but neglected fact, is that we spell it logistics, we pronounce it bullshit. The bullshit part of machine learning dominates the cool part, which is good news if you don't have a PhD, bad news if you do have a PhD. Because the cool part that they told you would get to do, you get to do very little of. On the other hand, if you're really good at plumbing, you've got a hell of a future in machine learning. So, like I said, it's either good news or it's really, really bad news, depending on your robust self-image. Some of us are very robust because we've worked in programming for a long time, which should be the most depressing job ever. They give you something that's broken and say, fix it. And they don't say how. So you work on it, you fix it. And as soon as you almost get it to work, they take it away and give you something else that's broken. So all of your life is surrounded by broken things. And you're supposed to survive that. That's the depressing part of programming. Well, it's even worse with machine learning because it's hard to get the data, it's hard to get the truth. And then it isn't just one model. People imagine, I'm going to build the model, and I'm going to deploy the model, and it will solve the problem. And again, logistics. That's exactly what that is. You can't just train one because you don't know what you're doing. By definition, if you knew, you'd write a program, not build a model. So you can't build, it's just like potato chips. You can't train just one. And so you got to train several. The first one will teach you something, And also the next day, the adversary, if you have an adversarial situation, like if you have customers or something that you're trying to entice into buying something, they will change. Your competitors will change how they influence the market. The world will change, so you'll have to build another one. And then you'll learn something new again, and you'll say, oh, I could do better. I'm going to build another one. Pretty soon you have a dozen models. And some of them you're just trying to keep in reserve because you might want to go back to them. Some of them are new, and you might want to go to them if they prove out. And one is the current champion. And then somebody says, oh, well, that was grand. Can you do this too? And that, and that? And pretty soon you have 100 different tasks that you're mediating with these models, times 10 versions of every one. You suddenly are managing thousands of models. You thought it was like homework where they said, here, build a model to do this. And it's nothing like that. You suddenly have thousands of these that you're not quite sure how they're working. You have to gather evidence. You have to make a statistical judgment, which is the best. And it's a whole lot harder than it looked at the beginning. And it's certainly a whole lot less glamorous. So we have to gather that information about what's working. And we have to do that a lot. Now, of course, then it gets worse. This is programming, right? I told you how that works. And so what happens is you hire some bright spark with a brand new shiny PhD as opposed to your corroded one. And you know, you get jaded after a little bit. But the shiny person wants to use a new tool because it's cool. Everybody wants to be cool. And then the next person has their favorite. Now, some of these tools really are better. Some of them might be better. Some of them might just teach you some clever trick. So up until just a very, very few years ago, all of the major ad targeting models in the world were running on something as simple as what's called linear regression, or logistic regression, which is basically just a linear combination of inputs. How is that possible that well after the invention of deep learning and all these tree-based methods, how could it be that that simple technique was still being used? Well, one, it's blazing fast. Two, every time some other more complicated model outperformed logistic regression, somebody went in, reverse engineered it, and says, it found that this followed by that is a good feature. Okay, I'll steal it. That became a feature to linearly combine, and the logistic regression worked well again. And so this progressive learning is a really, really big deal. And that's all about the logistics. So how do we do that? How do we do that? Some other gotchas. It just keeps getting better or worse. To build a real team, you have to have different personality types. Somebody who's an innovation seeker, a wonderful inventor, great person to have on the team. Terrible person to have on the team at the same time. It's really good to have somebody finding new stuff, finding new ideas, and it's really bad to have somebody whose fundamental drive is innovation when the system has to stay up. Because, of course, you want the system to be as absolutely boring as possible. You do not want excitement in terms of operations. So you need somebody who's operations oriented. They are absolutely not innovation seeking. They do not like excitement. They want to get it right. So you need those ops oriented people. You need the data science innovator types. And neither side is going to get it with respect to the other. So we have to build a system that makes both of these people successful. That's a trick. And here's a little preview. What I'm going to recommend here is something that we call the Rendezvous Architecture. It's an example of a streaming architecture showing how streams are very, very useful, but it also shows how we can make these teams work well together and how we can solve pretty much all of the problems. Well, you can't solve them, but you can have tools to mitigate the difficulties of all of the problems that I've described. So it is a stream-first architecture. That means that streams are a fundamental and prominent part of it. It's a microservice. Microservices allow, the fundamental definition of that is they are services, and we don't really define that. Services that can be deployed independently. Take them up, take them down, without degrading the rest of the system. And this system has that in spades. And it also is very, very container friendly. This is good because you get yet another t-shirt you can wear, and also good because your system can be more manageable. Now, what we're talking about here is only appropriate for certain situations, a very broad swath of situations, but not everything. It's really good for decisioning engines. That could be ad targeting systems. That could be churn prediction, marketing prediction, especially systems that have an SLA around real-time response, and especially about systems where you need to churn the models in order to find the best ones in the current situation. It is not necessarily so great where there's a huge amount of context. So if you have a self-driving car, there's hundreds of megabytes of current state. And if you were to do that as a question-answer sort of thing, you would have to provide, suppose you have a car in this hundreds of megabytes of state. It's on the road, it's turning, it's noticing a bump, and it has 3 pedestrians in front of it. Suppose you had that, what would you do? That would be the question-answer form of that, and as state gets very, very large, that becomes infeasible. And this becomes inappropriate. So we have a model. We ask it a question, and it gives us a response. That's what we want to build. But remember, we want to have multiple versions of it. There's a lot of things we want to do. Typically what happens when people start saying, I need to manage the logistics of models, is they say, I'm going to use a load balancer because that worked when I had ordinary software to deploy. And my load balancer, I could deploy a new version, and then I could tell the load balancer to start sending all the traffic to the new version, and there would be a data tier behind that to handle the state. It worked before. It kind of works with machine learning, but it kind of doesn't. The reason it doesn't is because only one model gets an input at a time. That means we don't get to find out what the other models would have done. That means if the Model 3 happens to be very accurate but not very reliable, somewhere down the line we decide Model 3 is not going to give us the answer in time, it's too late to ask anybody else. So there's a number of reasons why this load balancer style, which is so successful in ordinary code, is not so successful in models. You could do it, but it isn't really the best way. Now, if we had a stream, just imagine, if we had a stream where all the requests went, then a bunch of different models could read the same input, exactly the same input. That would solve the problem of the one model committing to an answer, because all the models could produce us an answer in the same time frame. So there wouldn't be a question of having to start over too late after we decide one of them is not going to give us the answer, because all of them started at the same time. This is called speculative execution. We go ahead, and you know, this is a symptom that I like to think of computer science was really a theoretical discipline until around the year 2000. To a very close approximation, we didn't have computers until about then. The computers we had were just barely better than rocks banging together. You laugh. That phone is like 10 times faster than the Cray 1 and 100 times more memory. I remember when that was a big deal, partly because it kept your seat warm, but that was a big, monstrous thing when it was first delivered to Los Alamos. And now, no big deal. So we have the power for many, many applications, not everything, but for many, many, a large fraction of machine learning uses, we could just run all the models against all the input every time. And we know then one of them is going to be very reliable, like the logistic regression, but perhaps not as accurate. The new one that the guy claims is awesome, maybe it's not so reliable. But we can get the best out of all of them if we could have them all try every request. But then we have a problem. How do we get a response? We now have 3 responses, not 1. We don't want to just commit to picking one because we're back to where we were. And so what we do is we put all the answers in a score stream and have what's called the rendezvous server. It sees the original request. It starts a timer, and it has a schedule of priorities. It says, perhaps, Model 3 is the one I truly, truly love. I will wait for Model 3. Well, I'll wait until I begin to panic a little bit. And then if Model 2 or 3 give me an answer, I'll be happy. Model 1 is just there for reference. Oh, at 3 milliseconds before the deadline, I will just totally ignore everybody and give a default answer. No, it's not fraud. That way I can guarantee that I meet the SLAs. And I can also guarantee that if the really good model gets its act together and gives me an answer, I will use it. And I can guarantee that even if it goes off the rails and cannot do that, I will still give an answer within the SLAs that's as good as I can. It's really kind of cool. Furthermore, if one of these things just goes out to lunch, no big deal. Its answer won't arrive, and we can just continue on with the others giving us answers. So all the models see all the inputs, and identically. There's no race conditions here. They get exactly the same input. So we have no question of exactly what they got, because we know they got the exact same thing. And we know now, we don't have to make these assumptions about if everything were equal. We know everything was. All models are in a fully production setting. We can put a model into production with no harm, no foul, because we will ignore it. Once we've seen it be stable, once we've looked at that stream of results and decided it's good, we can stop ignoring it, which is the tiniest, smallest action to deploy something that's possible. That means we're not going to screw it up. And not screwing it up is a big part of the game. The rendezvous server will decide which scores to ignore, and that means the rendezvous server is the focus of reliability, and the models are the focus of accuracy. What that means is that the ops-oriented people have a place to focus their efforts, and the data science people have a place to focus their efforts. Each one has a specialization so they can shine in their own way. Now, we can also add external data, like a user profile or a sample of measurement from the outside world, but we do that before the input stream. So all the models still see the same stuff. We can also add what's called a decoy model. It looks like a model. It sits there like a model, but it doesn't quack. It's a decoy. All it does is archive data. That is exactly the data that was seen by all the models. So recording all the data is a big deal. I have been screwed more times than I want to count. Perhaps I could count them, but I really don't want to enumerate them all. So for instance, we built a model one time. The bank gave us data. We built the model. We went back to the bank and said, we are the smartest guys on the planet. Our model is 10 times better than your model. We can detect fraud. And then we looked into the model, and it turns out that if you did not know the gender of somebody, the probability of fraud was much, much higher. I should have been suspicious. I was not nearly suspicious enough as a young person. And what that really meant is that if the account had passed an initial screening, they went on and gathered the gender information. And so by simply looking at was gender known, we were replicating the initial screening in a very elaborate machine learning kind of way. And what that really meant is that somebody was going back in and adjusting the database of what was presented to the model originally with what was known later. This is called a time machine leak, where somebody fixes the data for you. You had some defects in the data originally, they fixed it for you. They're so helpful. And the result was, when you trained your model, you had completely unrealistic situation in hand, and so you built a model that was as bad as mine. I am smarter now and very much more suspicious, so I want to record exactly what the models see. I do not want any race conditions. I do not want any optimism. I want those to go into a read-only format and not let anybody fix them for me. Now, we can also build a system called a Canary. Again, it looks like a model. It sees exactly the same inputs. It is, in fact, a model. It is a model which was good at one time, but whose only real virtue now is that it is exceedingly stable. We don't change it. And because it does not change, it is a wonderful reference for comparing other models. It is also a reference for the real world. Now, there's a philosophical bit here that if a model makes an interesting real-world decision, then it is understanding something about the structure of the world as observed by the variables we're giving it. And that means that the statistical structure of the universe is encoded by the score distribution on the output of that model, or perhaps a few models taken together, which also means that if that distribution changes, the world has changed in a very sensitive and semantically appropriate sense. Because that model understands the structure of the universe as appropriate for the semantics of the decision we want to make, changes in that distribution mean an important change has happened to the world. And that's a big deal. The Canary can detect both of those things, model errors and world changes. Yeah, Greg.
Wouldn't your current real model also detect changes in, if the data is non-stationary, and it's changed since your training set of the real model, or which is more recent data, or if it's changed since the Canary training data?
Yeah, the real, he asks, wouldn't the real models also change? Yes, they would. But the real models are by definition much newer than the Canary.
Oh, so assuming like,
And so we don't know what change means. We just put a new model up and it looks different. Well, it's supposed to look different. We put a new model up there on purpose because of that. And so we can't really say what does change mean, or does change even exist if we are churning through those new models quickly. It's only by having one very long-lived model that we can make that sort of distinction about what does change over a long time mean. Now, we can fairly quickly say, hey, this model's very much like the Canary by looking at the delta. And it seems to improve the Canary in these certain ways. And now look, it saw a change, which we know is a change because it's close to the Canary. Well, we might as well look at the Canary to do that. So it's the matter of experience and length of service that distinguishes the Canary in helping us find anomalies and changes like that. I should have said that on this slide. But anyway, the other things we can do is we can tap out using, tap out's the wrong word because that means surrender. Excuse me. We can put a tap on the data streams and we can sample the model inputs down here. Forget that part over there. We can just replicate the model inputs and we can into a development environment. And then we have something in development that we could debug or anything, but it's getting very, very realistic sample data because it is the real data. That's why it's realistic. Now we could also move upstream and replicate the raw requests and do different real-world variable imputation to try to model that as well. And we can do it in a completely safe way. As a person who has done some really profoundly amazing screw-ups, I'm big on this, we can do it in a totally safe way. Some of us, novelty seekers, need boundaries. At least that's what my mother told me. I needed boundaries. So this is the system. There's a proxy there at the beginning, puts things into streams. We add variables. I didn't really show that. We give it to multiple models. Some of the models are fake. The scores come out. We select which one goes into a result stream with a return address from the proxy. And the proxy there changes synchronous requests into streaming and talks to the outside world. We can have as many proxies as we like. Each one would put a return address for the result stream. The input is a stream so that we can see identical inputs. The output is a stream so that we can see all of the results as they come. And the rendezvous server is key to balancing reliability and accuracy. And the results stream is how the results come back out. Now, conditions will change, as Greg mentioned, and as I've certainly seen happen. And the key thing is to help us define that trade-off. Normally, the same rendezvous schedule will apply to everybody, but nothing prevents us from injecting a rendezvous schedule directly into a request and letting that override for the duration of that one request the nominal default system overriding thing. And we can do interesting things like A/B testing. We can do diagnostics so that this one request don't ignore Model 3, everything else does, and so on. So we can do a lot of that. Now, normally overrides would be unusual, but they could be quite common in an A/B sort of test environment. We can scale this up in a number of different ways. One, we can have just multiple rendezvous systems. And for that, it's really nice that streams go into a directory, because you could have the 3 streams that are involved in the rendezvous in a directory next to a file, which is the rendezvous schedule. And that could be a rendezvous system that we run on. In another directory, we can have another. Directories are a brilliant invention that is now only 50 years old, nearly. 1969 or whenever Unix really came up with directories and said they should hold all kinds of things. And then for a minor lapse of 50 years, people said, oh no, only files and directories, and maybe block devices or character devices go into directories. But we had that fork in history. It's one of those wonderful science fiction time machine sort of things. We had a fork in history roughly 1969. The System R crowd, Cod and all of his pals, were building the first relational databases in a timeline, in an alternative universe, at least it looks like it to me, an alternative universe that didn't have directories. The Unix world, in their timeline, in the timeline I lived in, directories were everything as the core fundamental organizing principles of a computer system. And we have gone with separate timelines from then until now. Databases still don't live in directories. Well, I think streams and tables should live in directories. I think it's insane that it's taken us 50 years to realize that. And so it's really, really cool when we want to run multiple rendezvous models to be able to do that. Now, we can also get more throughput. One of the ways we can do that is we can have very, very fast default models, possibly even one that just says no, 0 time for that. And that allows us to have the good models work most of the time, but under a flash load, the good models can just work as many requests as they can and skip through the rest. And the fast models will still catch up all the rest. And then there's extreme things, and we can show some examples of that. So here's an example of the fast throughput through failure. Suppose that we have one model that'll do 10,000 evaluations per second. One of them will only do 1,000, and we get a burst of requests at 2,000. Well, the slow model is not going to be able to do it all. Now, we may be able to scale it up or something like that, but in the moment, the slow model is going to be able to do roughly every other request. Well, that's just fine. We're going here. Suppose that Model 2 is the fast one, but we don't really want that one normally. Model 3 is the slow one. Well, a request coming through will hit both of them. Model 2 will answer instantaneously, but we won't use it. We'll just hold its result. Model 3 will answer in good time, and we will use its result. But the next few requests will come in too fast for Model 3 to handle. And so those, Model 3 will be as if it were out of action. The fast pass-through, Model 2 will still be able to handle those. And so the rendezvous server will be sitting there looking at the scores and saying, Model 3, great, we got you. Model 2, good. And then when Model 3 comes up for air, it will be able to say, oh, I'll just skip all the pending requests and only evaluate the last one. And that lets us, by having a default, automatically be resilient to overload situations. No action required, and we do as much as possible with the high quality model, and we do whatever necessary with the lower quality model, automatically with no action. Now, there are limitations. This idea of always evaluating everything with every model is kind of nutso. Well, it was nutso 20 years ago. It's only kind of nutso today. Most applications, it's fine. 95% of the times I've seen, it's fine. Sometimes it's not. And so we may want to do partial speculation. You know, in the extreme, we might just say on the new models, do 1% of all evaluations. That means we have only a 1% penalty. And we have only a 1% overlap for comparison, and we actually have to do something to fail over, not so good. Also, frankly, who here has worked at a startup? Anybody here? Anybody here implement the ideal product the first time around? Anybody who did that and then survived as a startup? No, of course not. You build something that's as horseshit as you can get away with. We call that minimum viable product because the business people can make an acronym out of it. But we try to be realistic when we're starting up a new business and only do what we gotta do. And this may be overkill. And don't kid yourself. How bad is it if the system goes down? I was building a video streaming system one time, and we were doing great. You know, YouTube and we were the top in terms of engagement and things like that. And I said, well, we can't do this because then the system might go down. And you know, my co-founder looked at me and says, so what? It's not like any money's involved, right? Like for an hour, people wouldn't be able to watch sand painting or something. It really didn't matter that much. Now, we didn't go down because we didn't want to, but it was always an option to build a system that was not really fully baked in order to meet the customer needs. So don't kid yourself, build what's right and realistic in the moment, which may be a rendezvous system or it may be something simpler. The context it just may be inappropriate to do this. The context may be too large. And the latency limits may be too stringent. I was watching a presentation from Jane Street in New York, and their big trading system had an SLA typically of 20 or 30 microseconds. Well, these persistent queues and stuff like that, they're awesome, and they are not going to get you to 20 microseconds. Some systems have to be that fast. If you have to be lower than a few milliseconds, this approach isn't going to work, although there has been an implementation of Rendezvous that uses ACA instead of streams. Loses a lot, but it gains the idea that it could go much faster. You lose all that persistence, but you do get the advantage that it's direct connect, and so could be very fast. Ad targeting is a great example of something that's just going to be too fast, probably. Suppose we got 10,000 requests per second. Typical way that these things work is circle number 1 represents a pre-selection of about 1,000 candidate models, candidate ads, out of hundreds of thousands, maybe millions. Then we evaluate a probability of click for each one of those 1,000. That means 10,000 per second times 1,000 evaluations. We're looking at 10 million evaluations, model evaluations per second. If those models are at all complicated, 10 million is a big number. And if we want to say multiply that by 5 because we are so loosey-goosey with our compute budget that we want to do full speculative execution on 5 versions, you're not so. You know, we're not going to do 50 million per second because 10 million was already a big number and our budget's probably limited. So that's probably not so appropriate. And in fact, what happens in these systems is that they use kind of the opposite of speculative execution, and they say, as soon as like 80% of the model evaluations that I need have come back in, go for it. If you get 80% of the 1,000 evaluated, let's go. And so they do just the opposite. And you can do partial rendezvous on this, where you do some speculative execution, but it's not the classic best point. The other thing about that is the latency guarantees may be very, very short, and so you may be pushing it to try to do all of that streaming stuff. So we're coming toward the end here. There's things we can do to deal with these very, very high situations. My guess is there's very few people in this room who are in the area where they need to make those compromises. I think that they can do this. I think that the rendezvous with the proxy, getting the inputs, putting them into a stream, models putting the results into scores, rendezvous picking one of the scores and ignoring the rest and putting it into a stream to result is a very viable approach that gives us a lot of benefits. It lets us have models in the wings so we see how they really, really run on real production load, on real production hardware. It lets us do hot handoffs with zero downtime, zero missed transactions. It lets us deploy things like decoys and canaries. These are very cool. And these are all described in the book, along with more stuff, because it's a book, not a talk. And you can talk to me now or later, depends on how shy you are. I'd love it if you talk now, because the questions are always the best part of any talk. So please feel free to ask. And I'd love to engage on this. We have people who are contributing to open source implementations of this, and all kinds of exciting stuff happening with Kubernetes, containers, streams, machine learning, all kinds of stuff. Yeah. Yeah, so the question is, how in the world do you keep all these models compatible? And it's actually kind of cool, and this is an important thing. So here's the input, and it's got to be consumable by all of the models. Now, some models are going to want to use some features. Other models are going to use other features. After a short period of time, there's going to be a lot of overlap. And so what I suggest that the right thing to do is put the union of all features into that input. The union means that any model you know about, and hopefully the union historically as well, any model you knew about, as long as the features are not so expensive to compute, you have them available. Now, with one caveat, that's especially for features that cannot be recomputed. Features that depend either on the request or on the request joined against the outside world. Say a user profile vector, that would be something you would need to inject there. But if it were simply, what is a person's average spend over the last 5 minutes? Or their card velocity. These are something that is internal to the stream and could be recreated very easily. So we don't necessarily need to inject those, but if more than one model does use those variables, it pays to put them into that input stream. So there's two kinds, extrinsic features and intrinsic features to the stream. Extrinsic, which belong somehow to the outside world, intrinsic, which are purely based on the contents of the stream, and hopefully short-term state. Those could be recreated within a model. All extrinsic features should, I think, be in the input stream. Yeah?
So I have a question. I have a question about the streams themselves. It sounds an awful lot like a pub subsystem. And that being the case, how do you deal with the semantics of within the topics issue?
The man has an august color of hair, and he remembers the word pub sub. And so the question then is the semantics of that. The traditional semantics of pub sub is that when a message is consumed, it is consumed often, unless there are multiple subscribers and so on. So what exactly do you mean by semantics?
I mean, many of the pub subsystems, the topics are produced free form, and somehow the subscriber has to end up parsing it. Or do you envision that there's some ontology for each topic that you can depend on?
So, yeah, the question is, how do you figure out what does the input look like? Not really so much the topics, meaning the topic names, but the contents of the topics, the requests themselves. Yeah, you have to have some convention.
You don't have that as part of it.
I don't much care. And people have very strong opinions, and so I especially don't care. I tend to go with the simplest possible thing. JSON, hey, just deal with it, self-describing. Maybe not JSON literally, maybe message pack or something like that. And if you want a little bit more control, talk about protobuf, talk about some of these other systems, which are not quite as self-describing as JSON or message pack. But you do have to have conventions. The variables have to come in a way that models can use, and they have to have names that the models expect. If I say it's over 35, and I spell that with a capital letter, and the model breaks. That's exactly what's going to happen. Now, in machine learning, the model space, the variable space, might be slightly hierarchical for nuanced interpretation, but generally, really, it's just usually a flat space. And so all that really matters is we have some namespace of features within a message that are consistent. We don't usually care too much about real data types. And the problem's usually pretty simple. Now, once you get crazy about this stuff, once you've got, like one of our customers has 1,400 data scientists, like lordy, and they're building models all the time, and they're very powerful and very effective. They have 10 times lower fraud than other people in the industry. At that point, and they don't do this yet, but I think that's crazy. At that point, I think that there's a lot of tribal wisdom that may be lost, which should be gained, in that you should put social credit onto different variables. This variable was used in 10 really valuable models. That's cool. This variable was invented by somebody who has built some really valuable models. And so the variables themselves should start getting preferred contexts and preferred values so that you can recommend them. In the beginning of model phase, you say, okay, I'm building a model to market to young people in the East Coast. You've just described it, your intent. And then the system should look at the words you used and say, those words are similar to the words used in models that are valuable and have these features. And it should say, hey, here's 40 features that might be useful to you in rank order of descending value, demonstrated value. I go, shit, yeah, use them, plug. And I build my model just right then, and then start looking at it. And then I start adding my own cleverness, and hopefully I get up on the leaderboard, that sort of thing. I think that you can use kind of internal Kaggle and combined with social credit on variables to manage some of what you're asking about. And I think once you have 1,400 modelers, geez, they're spread across 3 continents, you've got to do something other than just hoping that they'll talk to each other, because they can't. They're in the wrong time zones. Yeah, Hamid.
Yeah, so I wanted to ask a question about the model drift. So
Yeah.
given that is a real-time system, and we're in a hurry to keep up with the changes happening out there, and we need to detect the model drifts, and then in a hurry, we need to deploy probably some more over there and compare it to what's happening.
So he asks about model drift. And model drift, of course, is a misnomer. The model doesn't drift, it's the world that drifts. The world changes around us, and of course, we would like to blame the model, or at least our manager would like to blame our models there. And what we have to do is we have to, A, detect it. So that's where the Canary comes in. We have to detect world change and model failure and distinguish those as quickly as possible. And we need to have as many models on deck ready to roll against our idea of which directions the world might change. And we have to be able to deploy a new model as quickly as possible, even though we do not trust it yet. So we deploy this new model, and we don't know if it'll stay up. We have never tried it at volume, but we think it will mitigate some critical change, some new attack, say. Get it into production as soon as possible with a previous model as its backup. So we can push it out much faster in a much less reliable state if we know that our risk is bounded. It will be no worse than what we have now, because we will detect really egregious misbehavior quickly, and it will hopefully catch the things it was designed to catch And even if it crashes, some other model will pick up the slack. And so we are, the cost of innovation is the cost of failure, not the innovation. If we can put a lower bound on the value of failure, I mean the negative value, that means we can innovate much more rapidly. That means we can adapt much more quickly. The guys at Apple Pay I was talking to a year ago or so, they said, 20 years ago, fraud models were revved on 6-month cycles. And that was because fraudsters had to talk to each other face to face to communicate new methods of fraud. They had a very slow propagation system. Now, the major fraud actors can be a single entity that is spread very, very widely in a semi-automated way, and they can change in minutes to hours. And so the update cycle has to be much, much faster than it used to be. And they said that they were seeing radical changes in tactics from attackers on the scale of 6 hours. And so they often had to deploy new models. Now, if you're going to deploy a new model, do you want it to be the model? Or do you want it to be a model with 3 backups? I want to be able to deploy without worrying. So I want to have the backstops. Yeah.
Is it meaningful to have a confidence limits on the models, with respect to a given input that's coming in at a given time, and that confidence limit automatically, gives the deviation of what's it deviates from this confidence limit, then it could be 90%, upper or lower.
So the question is,
you can kick.
the question is really, if I express it more generally, is it desirable to have automated systems that will kick out a model under certain distributional assumptions? It is highly desirable to do that. It's also not always very plausible because Murphy is infinitely inventive.
Yeah.
Now, that said, if you know the Canary is a good, stable, old standing model, then you know anything whose score distribution radically differs from the Canary cannot be good. And so that right there gives you some of those bounds. The distribution of scores from a new model must reflect somehow the basic behavior of the Canary. It cannot be radically different, especially if most of your connections say not fraud. Yeah.
I have a quick question. If these guys are able to respond in 6 hours, do you have any idea as to what the processes they use for their development?
The good guys.
The bad guys.
So you're asking about how do the bad guys work?
Yeah.
Well, I used to catch a lot of shit for saying that my company was a leader in identity fraud. And the correction was always a leader in identity fraud detection. I've always been on the good side.
It seems like the guys are doing pretty good. What's their model?
Their model, see, the payoffs are radically different. The cost in most situations of attempting fraud that does not work is very, very low. Partly because, do you want to go get in somebody's face about something that might have been a mistake? Now, I'd rather just deny the transaction and not actually be physical about this. And so the only real risk
The cost of failure is low and the price of success is very high, so as a result they can afford a lot of failures.
Exactly. The bad guys have exactly inverted situation relative to the good guys. And so their innovation payoff is very high, and their innovation cost is very, very low. And so they randomly innovate in many, many cases. They just try all kinds of crazy shit. And then if anything gets through, they stop and they look at that. It's just classic evolutionary sort of behavior. Often, frankly, their systems are really, really stupid, and they make incredibly stupid mistakes. But it doesn't matter if they keep at it. Now, that's the traditional view, that as defenders, we must be perfect. We cannot fail. But the world is changing. As we gather more information, it is becoming a little bit different in that we can extract a whole lot of incidental information about a transaction coming in. IP addresses, forwarding chains, what do the headers look like on the request, things like that. A friend of mine was able to stop a major denial of service attack, but because he noticed that real requests had the char set accepted and the language accepted headers in one order, and the attackers had them in an opposite order. So he was able to filter those out perfectly. So the idea here is that with enormously larger amounts of data, what we can do is push the onus back on the bad guys, so they have to be perfect, and we can detect their defects against a standard that they do not know, because we don't even know it. It is accidental based on our network configs and things like that. And so that's one thing we can do. But the other guys have a very, very high innovation. If you can call the slop level that they do innovation, it's kind of like human innovation, genetic. So the question is, well, you notice I didn't say anything about how the models were trained. They could be supervised, they could be reinforcement learning, they could be completely unsupervised anomaly detectors. I really don't care. Now, it is true that their scores do not have to be calibrated against each other and therefore identical. But if we rank order them,
but the modes are different. I mean, the bumps are completely different. How would you score them?
Suffice it to say, they have, if you have a model that's useful, it's going to be pretty darn accurate. And therefore, its residue against the truth is going to be small. Any other model which is comparably accurate is going to have a similarly small lacuna in its knowledge. And that means that however we want to sort these things, as long as we can do a rank independent or rank order statistic comparison, we don't really care about the details of the shape. It's a topological comparison. And so we can now look at the fundamental significant differences rather than the accidental differences of score calibration. And we can do that. Look up QQ diagrams and you can see a lot about how that can normalize away the detailed metrics and leave only the topological comparisons.
So thank you very much.